Today we are going to explore probability, but not the typical schoolbook version. We are going to learn probability in the language that quantum computing actually uses: vectors, matrices, and transformations. Before we get to quantum probability, before amplitudes, before interference and superposition, we need a solid foundation in classical probability, because classical probability is the foundation and quantum probability is the extension. If the classical part is clear, then quantum will feel much more natural and less mysterious. In a classical computer, a bit is always either 0 or on, no uncertainty. But in real life and in probability theory, things are not always that clean. Sometimes it can be the bit is 0 with 70% probability and the bit is on with 30% probability. This is called a probabilistic bit. A probabilistic bit does not store a definite value. It stores a distribution over the two possible values, just like a coin. For a fair coin, the probability can be 50% of being heads and 50% of being tails. And a biased coin may be 80% head and 20% tails. And the rule that must always hold is probability of being 0 plus probability of being on is equal to 1. Probabilistic bits are like the classical cousins of qubits. Qubits generalize this idea, but instead of real probabilities, they use complex amplitudes. We can describe a probabilistic bit using a vector. This vector tells us the top entry is the probability of being 0 and the bottom entry is the probability of being on. Now for a coin, let's assume head is 0 and tail is on. So a fair coin can be represented as 50% probability of being 0 and 50% probability of being on. Similarly, a biased coin may be 80% probability of being 0 and 20% probability of being on. A coin that is definitely 0 has 100% probability of being 0 and 0% probability of being on. A coin that is definitely on has 100% probability of being on. Remember that the summation must always be on. You can think it as the classical version of quantum state vector, except classical uses real probabilities and quantum uses complex amplitudes. Now let's see how probability changes. A coin flip. Even a fair on is an operator. A fair flip always outputs 50% 0 and 50% on, no matter what the input was. We can represent this as a matrix like this. If we apply this to a definite 0 state, then we will get this. We transformed a definite state into a distribution. Now let's talk about a biased coin, which has 80% chance of landing 0 and 20% chance of landing on. As an operator, you can think it like this. This operator says, no matter what you give me, I output 80% 0 and 20% on. It does not matter whether your input was definite 0 or definite on. You will always get an output like this. This is the classical example of an irreversible operator. But remember, quantum gates are not irreversible. They are always reversible, and that is a fundamental difference. Let's generalize everything using stochastic matrix, which is the core of classical probability transitions. A stochastic matrix represents how a probability moves from one state to another. And here is the important clarification. A stochastic matrix can be row stochastic, where S row sums to 1, and column stochastic, where S column sums to 1. Both are valid. It depends on how you think about transitions. If rows represent the current state and columns represent the next state, then rows sums to 1. And if columns represent current state and rows represent the next state, then columns sum to 1. For our course, we use the row stochastic convention. For example, this is a row stochastic matrix, where S row sums to 1. This row stochastic matrix means if you are in state 0, then there is 90% probability that you will stay in 0 and 10% probability that you will go to on. And if you are in state 1, then there is 30% probability that you go to 0 and 70% probability that you stay in on. This is a classical transition matrix. A stochastic matrix is just a compact version of a probability tree. The matrix packs this entire tree into a clean algebraic form. Quantum mechanics also uses matrices for transitions, but the difference is that quantum matrices must preserve norm, not row sums. Now let's see how a stochastic matrix updates a state vector. If your current probability vector is P current, then the next state will be the multiplication of the stochastic matrix and your current probability vector. The probabilities in the resultant vector or the next state will still sums to 1. Remember that stochastic matrix always preserve the total probability. Now, what happens if you apply stochastic matrix multiple times, which is also called chaining transition? The result is also stochastic, meaning that if at the first step the stochastic matrix is P, then at the second step it will be P square, and in third step it will be P cube, and so on. So, stochastic matrices represent classical evolution. Now, let's talk about classical correlation. The idea that knowing one variable tells you something about another. For example, if two coins always land the same, then they are positively correlated. But if they land independently, then there is no correlation. And if they always land opposite, then there is negative correlation. We represent correlations with a joint probability matrix like this. All 4 entries are probabilities and the whole matrix must sum to 1. This is classical correlation, or you can think it as shared randomness. Later in quantum computing we will meet entanglement, which is a correlation that classical probability cannot explain. Understanding classical correlation prepares your intuition for that jump. Now let's summarize everything before going to the lab. Today we covered probabilistic bits, probability as a vector, fair and biased coin as operators, row and column stochastic matrices, probability trees, how transitions update a state, and classical correlation. These ideas are the classical foundation that quantum computing extends using complex amplitudes and unitary matrices. In this lab session, we'll take everything we just learned: probability vectors, stochastic matrices, biased coin, and transitions. We will actually simulate them using Python. Don't worry, no quantum yet. We are still building our classical foundation. But remember, the operations we do today are the same structure that quantum gates will use later. The only difference is that quantum computing uses complex amplitudes instead of real probabilities. So let's begin. I will start by showing how to represent a probabilistic bit using a simple NumPy array. Say we have a bit that is 70% chance of being 0 and 30% chance of being on. In Python, we can write it like this. This vector is your state. And we can check that it sums to on. Always make sure the sum is on. Now let's simulate a fair coin flip operator. A fair coin always outputs 50% of being 0 and 50% of being on, no matter what the input is. We write this operator like this. Now let's apply it to a definite state. Say the bit is definitely 0. So we get the output just like our theory. One thing I need to mention here is when you see the symbol @ just remember this. In our context, @ means multiply these matrices. That's it. So if you see something like A @B, you simply read it as A multiplied by B using matrix multiplication. We use this symbol mainly in Python, NumPy, and Qiskit. Now let's simulate a biased coin. We will create an operator that will take our current state to a biased state. The operator will transform our current state into a state which has 80% chances of being 0 and 20% chances of being on. So we can write the operator like this. Now apply it to our definite 0 state. and we can see the result exactly like the theory. Now build a row stochastic transition matrix like the one we discussed and check its row sum. You should see on and on, which is perfect. Now let's update a probability state with this stochastic matrix. At first we take our current probability state. Now apply the stochastic transition matrix to it and we get the next state. This is exactly what the math predicted. We have just simulated a on-step transition. We can also simulate it multiple times. This represents a longer time behavior, which is multiple jumps in the probability tree. Later in quantum computing, we will do the same thing with unitary matrices to simulate time evolution. In this lab, we learned how to represent probabilistic bits in code, how to build probability vectors, how to simulate fair and biased coins, how to construct and verify stochastic matrices, how to apply transitions to probability distributions, and how to simulate multiple steps of stochastic matrix. Now you have all the coding tools you need to understand quantum probability, which is coming very soon. And that's all for today's video. Hope you liked it. Make sure you subscribe the channel and like the video. Share this with your friends who are also interested. And until then, happy quantum computing.